Calculus Differential Equations. In the first section, we're going to talk about slope fields. The objectives are we're going to check solutions of differential equations. We're going to see how to use initial conditions to find particular solutions of differential equations. That's the plus C when we integrate. We will sketch the slope field of a given differential equation, and we will use slope fields to approximate solutions of differential equations. So, quite a few definitions to start with. An equation like dy dx equals y ln of x containing a derivative is called a differential equation. So, a differential equation is any equation that has a function and its derivative. Other examples of differential equations: y minus y prime equals 0, or a lot more complicated, y minus 2y prime plus xy double prime equals cosine x. So we're trying to find what function y would fit in the equation. When we find all the functions that satisfy the differential equation, we have solved the differential equation. For instance, for this differential equation here, maybe you can guess what the function is. The function y equals e power x satisfies the equation because the derivative of e power x is itself. So we would have e power x minus e power x equals 0. It's not the only solution. For instance, y equals 2 times e power x would also work. This one is a lot more complicated. It may even be impossible. The value of f of x for one value of x is the initial condition of the problem. Again, this is usually how to find the constant c. The problem of finding a function of f of x when we are given its derivative and the initial condition is called an initial value problem. And finally, when we find the particular solution that fulfills the initial condition, we have solved the initial value problem. So an important note here that shows how differential equations compare to equations. So the note says differential equations can be compared and contrasted with equations. It helps realize what is extraordinary about differential equations. So the first difference, obviously, is the field of mathematics. Equations is part of algebra and differential equations are part of calculus. An example of an equation, 3x squared plus 7 equals 14. We all know that the solution is going to be a number. Actually, it may be many different numbers. There might be many solutions. In this case here, 3x squared plus 7 equals 14. We know how to solve that. Subtract 7, divide by 3, and take the square root. So the solutions are x equals root of 7 over 3 and x equals negative root 7 over 3. Differential equations are different in the sense that the answer is not just going to be a number, the answer is going to be a function. And that's really amazing. We have an equation and we look for the function that fits this equation. In this example, y prime equals x over y. What function could we plug in here for y and plug its derivative here so that it would satisfy the whole equality? There is more than one solution. Here are 3. Y equals square root of x squared plus 1, y equals square root of x squared plus 2, y equals square root of x squared minus 5, etc. You probably guessed it. The general solution is y equals square root of x squared plus c. You can try to plug square root of x squared plus 1 here, then look for the derivative of y, plug it here, and check that it satisfies the equality. So this is exactly what we're going to do here. We will be given a function y, and we will need to check whether it does satisfy the differential equation. Y equals 3 times e to the negative x. Does it satisfy this differential equation? So we need to start by finding what y double prime is. If y is 3 times e to the negative x, that means y prime is negative 3 times e to the negative x. And if we differentiate again, y double prime equals positive 3 e to the negative x. So let's see whether it works. Y double prime plus y is y double prime plus y equals 3 times e to the negative x plus 3 times e to the negative x. That's 6 times e to the negative x. Does it satisfy my equality? Is it equal to 0? Obviously not. At least not for all x's. So the answer is no. Let's try with y equals cosine x. Again, I need to find y double prime, so I take the first derivative. Y prime equals negative sine x. I differentiate again. Y double prime equals negative cosine x. And now I plug it in my differential equation. So y double prime plus y is negative cosine x, which is here, plus cosine x, and that is equal to 0. So y equals cosine x is a solution of the differential equation. Yes. Question A here is very much the same as our previous example. We need to show that y equals c times e to the x squared is a solution of this differential equation here. So my differential equation contains y, it contains y prime. There is no y double prime here, so I'm not even going to look for y double prime. So y prime equals c times e to the x squared times the inside derivative, 2x. I plug everything in, so y prime over 2x minus y. This is y prime, I just found it, over 2x minus y, which is given, c times e to the x squared. And I observe that 2x cancel out, and then I'll have ce to the x squared minus ce to the x squared, so it's equal to 0, just like I was hoping. So I've shown that it is a solution. Now question B, find the particular solution that satisfies the initial condition y equals 3 when x equals negative 1. That's easy. We have the function already. We just plug in y equals 3 and x equals negative 1. Y equals 3, x equals negative 1, and this allows me to solve for c. So I can replace c with 3 over e, and I get the particular solution y equals 3 over e times e to the x squared. I can rewrite this, if I wish, as y equals 3 times e to the x squared minus 1. It's not necessary, but sometimes in MCQs this solution wouldn't appear, this one would appear. So we need to know the properties of exponents. Slope fields. A slope field is a plot of short line segments showing the slopes of all solutions to a differential equation. We will start by sketching one. Sketch a slope field for the differential equations x equals y prime plus y for all the points a, b, where a and b are integers. A is -1, 0, 1, or 2. B is 0, 1, or 2. So, on a system of axes, these are all the points that we need to study. A is the x value, -1, 0, 1, 2, and B is the y coordinate, and it ranges from 0 to 2. So for all of these points, we need to represent the slope by using the differential equation. By rearranging the differential equation, I see easily that y prime equals x minus y. So the slope of my solutions are going to be x minus y for all points in the Cartesian plane. For instance, at the point 1, 2, so I just picked one of these points randomly. The point 1, 2 is up here. At the point 1, 2, the slope y prime is x minus y, so 1 minus 2, which is -1. A slope of -1, we have a good idea of what it looks like. It is -45 degrees. It points directly to this point, obviously, because it's rise over run, which needs to be equal to -1. Let's try another one. At the point 1, 1 here, y prime is x minus y. Here 1 minus 1, which is 0. Again, a slope of 0 is very easy to represent. It's represented by a horizontal little line segment. Now you can do this for all other points. So we have 12 points total. Just, you don't need to write anything. You can do everything in your head and just add the line segments for each of these 10 other points. So once you are finished, you should get something that looks like that. It becomes a little bit more difficult to represent slopes when they are very negative or very positive. Don't worry about that. We can see here that this is steeper than that, this is steeper than that, so this is enough. You need to make sure that slopes of 0 are clear, slopes of +1 are easy to see, -1, but then in quizzes or tests, for instance, I wouldn't look whether this is exactly -2, but I would check that it's steeper than this, for example. So if we want to plot the solution curves of differential equations, here's a huge slope field. If I want to find which curve would be the solution going through a point like -2 pi over 2, I need to find the point -2 pi over 2. It's here. And then I need to sketch a curve that fits the slope field. So imagine this is kind of like water, and you throw a cork in the water. It's going to flow with the movement of the water, and the solution curve is going to be something like that. It's very important that you see I am never crossing any of the line segments. It's impossible to be crossing one of these line segments. Same through the point 1 pi over 4. Try this yourself. The point 1 pi over 4 is somewhere here. So find this point and try to sketch the solution curve of the differential equation through the point 1 pi over 4. This is approximately it, and again note how I'm never crossing any of the little segments. Sometimes I'm between, sometimes I'm almost on top of it, but I never cross through it. So we aren't doing Euler's method. It's not included in the exam either. So let's review our objectives. We first saw how to check solutions of differential equations. So if we are given a function like y equals cosine x, we can find y double prime, plug y and y double prime in, and see that it is equal to 0 like we want. We've seen how to use initial conditions. So if we are given a general solution, we can use an initial condition, here y equals 3 when x equals -1, to find the value of c. c is 3 over e, and then I can write the particular solution of my differential equation. We've seen how to sketch slope fields by solving for y prime and then plugging in values for each of the points in the domain specified. And finally, we've seen how to use slope fields to approximate solutions of differential equations. So that's it for now. Thank you very much.